All right, welcome back. In this video, we're going to be looking at some more aspects of basic probability. Previously, in the videos before this, we spent some time talking about counting and ways to come up with basic probabilities using, number of ways of an event divided by the number of ways of a sample space. And so we hit that pretty solidly. In this video, we're going to be looking at something that's a little bit different, and this is a very useful concept in breaking down bigger problems into smaller, more manageable pieces. Right? And so the topic for today is going to be conditional probability. All right, so as we start to set up for this, I'm going to make a few definitions just so that we have it. First one is that event A and event B are two different events. Okay, and we can say that there is a conditional probability of A happening given that B has already occurred, that is written as follows. Okay, so you've got a probability of A, and then there's this vertical divider line. It's not a mathematical operator, it's just a notation. So it's A given B, okay, is equal to then the probability of A intersect B divided by the probability of B. All right, and so of course A intersect B is the event where both A and B have to happen, and then B is the event B that we described before. All right, so just kind of give you kind of an example. It's kind of a strange concept at first, but once you get the hang of it, it's pretty easy to work with. So our example is we're going to toss a single die, and I see I have a typo. Let's fix that. Okay. All right, and again, some of the assumptions that we'll make on this are that we are equally likely outcomes. Okay, and so we're going to define event A as being the event where when I throw a six-sided fair dice that I get a number less than 4. All right, and so for A, obviously the outcomes that matter for A are the numbers 1, 2, and 3. So there are 3 ways that this event can happen on a six-sided die. All right, we'll define event B as being the number that we roll on the dice is an odd number. And so obviously for numbers less than 6, our outcomes are 1, 3, and 5. Again, 3 ways to be able to do this. So those are the events that we're looking for. The sample space for this then, for a six-sided dice, is obviously the numbers 1, 2, 3, 4, 5, and 6, or 6 ways. So with that at our disposal, we can use the rules of the previous couple of examples to calculate the probabilities of A and the probabilities of both A and B and probability of B and so on. So as you might expect, probability of A then is just 3 divided by 6. It's the number of ways of A divided by the number of ways of S. And if I simplify the math, I get 1 over 2. Okay, and this is what we call a prior probability. I can look at the intersection of the events A and B in this, and so remember, this is what they both have in common. So looking at my numbers 1, 2, 3, and 1, 3, 5, clearly number 1 and number 3 are common to both. All right, and so my A intersect B is the events, of 1 and 3. Okay, and so there are 2 ways that can happen. And so with that, then I can do the probability of A intersect B as being 2 divided by 6. So again, all we're doing is this guy is still the probability of my sample space. Okay, and so 2 divided by 6 is also 1 divided by 3. Now, something else to kind of point out as we're looking at this is that I can have the probability of the complement of A. So that would just be 1 minus the probability of A. So 1 minus a half is still a half. So we have that. Nothing real surprising there. Again, this is all stuff we covered in the last video. If you're struggling with it, then you might want to take a look at some of the older videos to get up to speed. All right. Okay. Likewise, do probability of B, 3 events over 6, 1 over 2. Got it. Okay. So now I can come in and I can calculate the conditional probability that basically says that given that my probability of my event B has already happened, I'll slide this down so you can see event B. So given that I have an event that is 1, 3, and 5 as my number, that I've rolled one of those 3 numbers, what's the probability that this was also in event A? Okay, and so if we look at it, we take our numbers, we take our basic equation, so we go back, and remember it's the probability of A intersect B divided by the probability of B. And again, the one that goes in the bottom is the given on this. So if we look at that, then we can take our numbers, and so I can say, okay, so the probability of B is the half that's here. The probability of both A and B is 1/3. So then the probability of A given B is 2/3. So the probability of me getting a number in A, if I'm already dealing with the set of B, is 2 out of 3, right? Because 2 out of 3 of these guys are located up in A. So that's what a conditional probability is. Now, like I say, the words of it and the equations are kind of a little may not be utterly clear on this. So what I did is, what we can do is we can come in and we can kind of redraw this thing as a tree diagram, and I'll show you that. Now, one last comment about A given B is this is what we call a posterior probability, as kind of a different term. So sometimes in your reading you'll come across those, and that's all we're doing with those. We won't spend a lot of time talking about prior and posterior circumstances. All right, let me see if I can get the light to not be messed up again. Okay, all right, let's try it. All right, so here's our tree diagram. And so what the conditional probability is, if you remember, is that we're looking for ways to move down these paths. So for our outcome A intersect B, which is this one, to get to this point, this exit point here, the only path that gets me there is I had to go up through A and then up through B. So I had to go through both A and B to get to here. Likewise, if I went up to A and then down through not B, then that outcome is A intersect not B. Right? What the conditional probabilities are the probabilities of each of these individual branches, that assuming that I'm standing on A, what's the probability that B happens? Okay, so when I do that, this is labeled as P, or the probability of B given that A has already occurred. And then likewise, I could be standing here, probability that A didn't occur, given B prime. And so you can see all of these, every single one of these is a conditional probability branch. And so it lets me take a bigger problem like this and break it down and start looking at just one of the legs independently, which can greatly simplify your problems if you do it right. Now, the first leg then is, obviously I started at S, so given that I'm in the sample space, then this guy, to get to A, this is the probability of A given S. Well, we just call that as the probability of A, all right, because clearly we're in the sample space. Okay, and then likewise probability of not A given S, but every one of these is a conditional probability. Now, the one thing to notice on this, and this becomes fairly important, is that we're always starting at S, and the way I've drawn this, we're moving left to right. I can't go the other direction. So on this tree diagram, there's no way for me to be able to find probability of A given B. It does not exist on this tree the way that it's currently drawn. So that is not an option for us to be able to work with. Okay, so basically the conditional probabilities are the probability of the branches between the different events. Okay, all right. So once I have that, then I can go in and I can kind of look at some other versions of the rules on those. Okay, and the first one that we have, get some of these cords out of the way. There we go. All right, is the multi-rule. All right, and so if we take our conditional probability equation and rearrange it a little bit, then I can say that the probability of both A and B then is simply the probability of A given B times the probability of B. Okay, and likewise, I can go to multiple events. Maybe I have a binomial tree that is now 3 deep, and I could do A1 intersect A2 intersect A3, then is the probability of getting A3 given that I've already come through A1 and A2, multiplied by the probability of A1 and A2. Okay, and then I can further break this guy down into being the probability of that first term, multiplied by the probability of the second term, multiplied by the probability of A1. Okay, and so that's kind of one of the things that we can start to kind of look at. It's kind of a cool little trick. Okay, and so this is what we call is a computation for calculating the total probability for an outcome is the product of all of the branches on the path. Right. So if we look at this one, that if I look, I have my A1 given S. This is my A2 given my A1. This guy is actually my A3 given my A1 intersect A2, because in order to get to this branch, I had to come through these two guys, right? And so all we're going to do then is, if I can figure out the individual conditional probabilities that satisfy those three requirements, then to get the probability of this event, I just take this value times that value. That's all it says. So this is where these trees are really, really cool. Okay, I can calculate, do whatever it takes to get those probabilities, and then I can come up with all sorts of really complex events in a hurry. The other thing that's really cool about about these trees and the rules that we're setting up is, let's say that this guy is 0.7. All right, because of the law of total probability, I know that this branch has to be 0.3. That these two guys coming out of a common source have to add up to 1.0. We have to account for all the outcomes. Now, I could have third outcomes, but the total of all of them ends up being 1.0. So there's some really cool features that starts to show up. Same for this. This could be 0.6, and that would have to be 0.4. so forth. This could be 0.5, making this one 0.5. All of the cases, these two branches will always add up to 1.0, just like these two will always add up to 1.0. Okay, now again, obviously I haven't drawn the whole tree just for clarity, but that's kind of the process that we're looking at with this multi-rule and being able to do conditional probabilities, okay? So ultimately, the technique is useful when events happen in succession. First I do one, then I do the next, and then I do the next. Okay, this technique is very, very, very handy. All right, so let's give one a try and take a look and see what we can do. All right, I get it down here. So one of the examples that we can look at is, what's the probability of drawing 3 consecutive aces out of a fair deck of cards? All right, so we're going to define our event AI, which would be I is the pull. So we're going to do 3 pulls in a row. So say the first pull would be A1, the second pull would be A2, so forth and so on. Is that we're going to draw an ace on the ith, what we call the ith draw. All right, so A1 is on the first, A2 is on the second, A3 is on the third. I can draw my diagram. This is just a repeat of the picture that you just saw. Okay, and so this is, you know, ace on the first pull. This is my ace on the second, and so forth and so on, right? So all I need to do is be able to come up with the probabilities that define this. And so then my outcome of 3 consecutive aces would be the one that comes out at here, right? Because if I got this one, I didn't get an ace on the third. And if I got one of the ones down here, I didn't get an ace on the second. And again, these two guys will go into A2 and A2 prime, and this goes into A2 and A2 prime also, all right? So we can work our way through that. All right, so here's what we're gonna do. So we're gonna use our law of total probability, and we're going to compute the probability of getting 3 in a row. And so all I'm going to do is I'm going to take the probability of this branch, multiplied by the probability of this branch, multiplied by the probability of that branch. Okay, so if we look at it, we can come in and say that the probability of A1 given S, since there are 4 aces at the time of the first pull, is 4 out of 52, right? So by comparison, the complement of A, given that I'm in S, is 1 minus that number, so that's a 48 out of 52, right? The probability then of A2, given that I already pulled 1 out of the pile, if I pull 1 out on the first pull, then there's only 3 that are left, and there's also only 51 cards left in the deck. Okay, and so you can see how these numbers start to change, but these probabilities, that's what we're calculating as the probabilities of the branches. And then likewise, the probability of A3, given that I've already pulled A1 and A2 on it. Now there are 2 aces left because I pulled the first 2 out, and there are 50 cards left in the deck. So these are the probabilities. So if I look at the branches, I can start to kind of write these things down that, you know, there's my 4 and 52. That was the number that we had here. Okay, my 3 and 51 is the probability of this branch. My 2 and 50 is the probability of this branch. Okay, and so what they are, the conditionals are just those little bitty segments that we're working with. And then if we take the law of total probability, then if this is 2 out of 50, this has to be 48 out of 50. And this is 3 out of 51, that has to be 48 out of 51. And if that's 4 out of 52, then that has to be 48 out of 52. And you can build this whole tree diagram with all these individual probabilities. And you'll notice for this diagram, every one of the branches ends up being a little bit different, at least for this problem. Okay, now that's not always the case, but in this example, it is. And so very quickly, I can come up and define the events. Oh, I have 3 in a row. I would do this times this times this, and that's the probability that kicks out here. Okay, we could come in and say, well, what's the probability of having, 2 good pulls? Well, there would be 1, 2, and a not. That's 2. I could do 1, not, and a good. Got that one. And then I would have a couple down on the lower side also that I could come out of here and go into a good A2 and into a good A3, and all those criteria would satisfy that question. Okay, so this is what conditional probabilities can do, and they're very, very powerful and leading us into being able to do some very, very cool things very quickly for our process. So I hope that makes some sense for us. Okay, all right. So now let's go rewrite that law of total probability in a slightly different form. Okay, that we talked about. So all we're doing is we're multiplying, for any given probability B, the B given A multiplied by the probability of the A. So this is just a shorthand way of saying we're going to multiply all of those branches together. The formal definition, as your book writes it, is if A1 up through AN are N mutually exclusive and exhaustive. Okay, now this is a new word for us, this exhaustive. What exhaustive means is I've accounted for all of the possibilities within a subset. Right, so for exhaustive on S means that S is then A1 union A2 all the way out to union AN. All those guys together add up to the sample space, that we haven't left anything out. all right, then for any event B, the probability of B is just simply the summation of all of those branches, I through K on this, B given AI multiplied by the probability of the term before it. Okay, so this is just a fancy way of showing you that tree diagram that I showed. And this is where I said, if you try to memorize formulas, you can get into some trouble on this guy. And so we want to be very, very careful on that. All right? In fact, that should probably be an N, not a K. Okay, so there we go. All right, now we talked about the one problem that we have with these tree diagrams, right? And that they only go in one direction. In the event of the tree that we showed back on that very first page, again, we were working everything from left to right, but we talked about not being able to find this guy. All right, well, mathematically, they've come up with a way to be able to do it, and this is known as Bayes' theorem. And it's probably one of the most useful theorems for dealing with conditional probabilities. So again, we're dealing with A1 through AK are mutually exclusive and exhaustive, so the same criteria on this, okay? That the probability of an event A, J, given that B has occurred, we know would be this equation. That's our basic probability equation, okay? But I can correlate this back then to also being the probability of B given AJ multiplied by the probability of AJ, because this term is common to both of those guys, right? That if I have the probability of B given AJ is equal to then the probability of AJ intersect B, okay, multiplied by the probability of AJ, right? That's the term that shows up on the top of this. So all we did is we rewrote this intersection because it was the same in both of the probability formulas. Okay, and I misspoke. That should be not times, that should be a divided by. There, this term is over that term by our basic definition, as indicated here, right? Okay, all right. All right, and so then all we have to do then is come up with, well, how do we come up with all of the probabilities of our event B? Well, this is that total probability that anything that includes a B we have to include. And so we're basically finding the percentage of the event that I'm looking for relative to the total of those. And I've got an example we'll work this. But the thing that's really cool about this is now you have an expression in which I have a conditional probability that is A given B, that now if I know this one, I can turn around and find the B given A, or vice versa. Okay, so it's a way of basically, in effect, what you've done is you flipped the tree and you're going the other direction with it now. All right, so let's give this one a try. So it basically reverses our tree direction. All right, so let's take a look. And I have a box of marbles. Okay, something fairly simple that we can kind of wrap our head around. And so I have two boxes of marbles. And this box 1 has 3 blue marbles and 2 red marbles, or 5 total. Box 2 has 2 blue and 5 red marbles, or 7 total. And we're going to take both of these boxes and we're going to dump them all into a pile. Okay. What we're going to do, our experiment then, is that we're going to pull a marble at random from the pile. Okay. So if the marble is drawn at random is blue, what is the probability that it came from box 1? Okay. So this will be the word problem that you might see on this. And so what this is asking us to find is, given that it's blue, okay, so if it's blue, what is the probability it came from box 1? So we're looking for the probability of box 1 given that it was blue. Okay. Now, if you look at the data, if we try to draw the tree for this, okay, based on the data that we have, one approach might be to come in and say, all right, here's my sample space. Let's break it up into the boxes, box 1 and box 2, and then in each one of these I have a blue and I have a red, and I have a blue and I have a red. Okay, and so we know then that this branch here is the probability of B given box 1, right? Okay, and just like this is the probability of R given box 1 for that branch. Okay, notice that this conditional is not the conditional that we're looking for. Okay, now calculating these is very, very easy, right? If I want the probability of box 1 given that it's, in the sample space, all I'm doing is I'm taking the fact that I have, if we look at this, I had 5 marbles in box 1, and I have 12 total in the entire sample space. So the probability that it came from box 1 is 5 out of 12. And likewise, probability of box 2 is the 7 out of 12. Okay, and again, this term plus this term is 1.0. So that's our total probability at work for us. Okay, now with the data the way that it was written, I can also calculate the probability that, given that it was in box 1, what's the probability that it's blue? All right, so all I do is I say I had 5 total in box 1, and there were 3 of those are blue. So my probability for this event is 3/5. Okay, and so the probability of it being in red in box 1 is then 2/5, and then similarly for the others, blue from box 2 or blue given box 2 is 2/7, and red given box 2 is 5/7. Okay, all of this is the data from the data that we were given, and it's pretty easy to calculate these. The problem that we have is that we're being asked to solve a question that wasn't set up by the data that we have. Okay, so the idea is that it's not the right conditional that we want, so we've got to flip it. Anytime we don't have the right conditional, we can flip it by using Bayes' theorem. So this is how it starts to work. Okay, so let's take a look. And so basically, in effect, we're going to change our tree. Okay, and so all I've done is, you notice now, instead of doing box 1 and box 2 here, I'm now doing blue and red. Okay, and then given that it's blue, box 1 and box 2, and given that it's red, box 1 and box 2. So you can see the tree is very, very different from the one that we just did. If you compare this, here's the original, and this is the one that we're now wanting, and this is the one that has the probability that we want right here. Okay, all right. So first thing that we're going to do is that we need to first compute the probability of it being blue, or that it's blue from the sample space. So all that is the total number of blue marbles over the total number of the sample space. So we had 3 from box 1 and 2 from box 2. That gives me a 5, and then the number of the sample space is 12. Okay, and likewise for the red, I can come up with that as being 7/12 in a similar fashion. All right, so all we do then is we use Bayes' theorem, and we basically rewrite this, that if I want the probability of box 1 given that it was blue, okay, all we're going to do is calculate the probability that it's blue from box 1 multiplied by the probability of box 1, and I now have all of those parts, okay, given the data that we had back on the last page. So again, I'll kind of see if I can arrange this where you can see it. Okay, so again, we had blue from box 1. Okay, now what has to happen in this is, so because we want the blue in box 1 case, I need that probability, kind of as a total probability of that event happening. But to figure out the total probability of this thing when I flip it around, I have to come up with this guy. Well, what is this expression coming? This was that summation in the bottom of the Bayes' theorem formula, the one that was, let me put that back up here. That's what's coming out of this. Okay, now again, as an equation, it's not completely clear what it is, but what it turns out being is if we go back to that original tree diagram from the data that we had, what we're doing is we're going through and we're finding all of the probabilities that involve this blue marble. Okay, so we're finding the probability of this guy and then coming down and picking up this guy. So what I know is I know that if I'm trying to find blue in box 1, I need to find the total probability of all of the blues. Okay, so I'm going to take this times this plus this times this, and that's all that we're doing on those. So that gives me the denominator, and then because I'm looking for this particular branch up here on our picture, okay, I just need to calculate the probability of that particular term, and so that's what we've done. Blue from box 1 times box 1 plus blue from box 2 times box 2. And I can plug in my math, and then 3/5 times 5/12 all over 3/5 times 5/12 plus 2/7 times 7/12 is equal to 3/5. Now, one of the things that's kind of cool, if you do this right, you'll notice that these two, the numerator here will cancel the denominator here. Okay, and that shows up in all of these positions. So that's a kind of a cool trick to help you set this up. So the probability then of being in box 1, given that I'm blue, if I do the math, is simply 3 out of 5. All right, so if I'm blue, it's a 3 in 5 chance of it coming from box 1. Okay, and so you can kind of see that if you look at this, because we had a total of 5 blue marbles, right? 3 of which are in box 1 and 2 of which are in box 2. So Bayes' theorem allows me to flip this tree diagram and start to kind of work it in a different sense. So 3/5 of the blue marbles are from box 1, even though when we set it up on that original first setup, it was the other way around that we were looking at. Okay? All right. So anyway, that's kind of the approach to conditional probabilities. I hope it hasn't been too confusing. The Bayes' theorem is very, very handy, and conditionals prove to be really, really useful. And as we get into independence and some other calculations, we'll start bringing those back around. But I at least wanted to kind of show you the basics of the conditional probability. All right, and so I hope that's been clear to you. So we'll end this lesson here. As always, please let us know if there's anything that you'd like to see or that we can do differently or to clarify down in the comments below. And of course, like the video, and please subscribe to our channel, and we'll keep the lessons coming. So anyway, I hope that works for you. So anyway, thanks for the evening. Have a good one. Happy engineering.